Good evening and welcome to your class of Introduction to Measure Theory. Today is the first part of the fourth lecture. Today we will talk about outer measures, also known as external measures. So let's go to the blackboard and we start this with a definition. The definition tells us that if we have an empty space and let's take its trivial sigma algebra, which is the power set of x, we say that an outer measure, which is also known as an external measure, is a function and the notation will be this one. Of course it could be any other, but this goes from the power set of x into the extended interval, such that the following holds. And we have three conditions. The first one is that the value of the empty set is 0. The second is that if we have two sets, they are both inside the power set, of course, then it follows that the outer measure of the smaller one is less or equal than the outer measure of the bigger one. And the third property, we have some countable sequence inside the power set, and then we have the subadditive property that you already know, this one here, and this is less or equal than. I ran out of space. So this is the other measure of this one. So from this property, it is clear that we can write it here that any measure on some measurable space x and power set of x is an outer measure. Any non-trivial, because you need to recall that we had a trivial measure in which any set was assigned with plus infinity. But besides that, that trivial measure, this was trivial. We have that for any measure, the value of the empty set is 0. And we also had this property here, the second property, the always hold, and the third one was called the subadditive property. And the equality was held whenever the sequence pair disjoint, but in general the subadditive property also holds. So any measure that is defined on this sigma algebra is an outer measures. So many measures won't be outer measures because the sigma algebra is some proper subset of the power set. So when that happens, we won't have another measure. But for the case in which we are taking the power set as the sigma algebra, we are in fact with an outer measures. It also follows that an outer measure is not necessarily a measure. So a remark here is also in order. Outer measures are not always measures. And why is that? Well, because we perhaps we won't have the additive property. This may fail property. So the additive property tells us that the value of the measure of the union, if you recall, of pairwise disjoint, they were pairwise disjoint, was equal than the value of this series, which may or may not converge, but in general we have that equality. So this may not work for any other measure. So this was completely additive. That was the full name, completely additive property. So this may fail for some other measures. Alright, so the following will be an important theorem. Let's go with this. That tell us that for any measure space, we have this measure space here. So this is a sigma algebra, which may be a proper subset of the power set. So this is our measure space, and we can define a function which we denote by mu star that goes from the power set into the extended interval, such that this function is an outer measure of x of this space. So this is important because we may have some measure of interest. We don't know which one it is. That is not necessarily defined on the whole power set. So from this, let's write it like this. This is a power set of x. X is here, and we have some measure defined on this subset of the power set. We have some measure here, and then we will extend this measure as an outer measure for every other element which may not be in the initial sigma algebra. So we will extend it to complete the whole power set of x. So it is very interesting. It is the proof will be constructive in nature. So let's start with this. Well, we can before that we can specify instead of proving the existence, let's say bluntly exactly which outer measure we are considering. So we will consider this outer measure. So let's say for any p in the power set, this function is defined as the following. So yeah, as I told you, the proof was constructive, and the heart of the proof was to construct it like this. So we can just enunciate it like that instead of working with an existence theorem. So now we will prove that the function defined exactly like this, it's in fact an outer measure. So let's begin. The first step will be clearly to prove that the definition is whole. So we will start with the first thing that we will make sure is that the outer mesh, the function mu star on the empty set is equal to 0. So let's see what happens here. By definition, this is equal to the infimum of every such that this is an element of the sigma algebra and the empty set is inside A. So this is trivial, this is also trivial. So it's just the infimum of every value of the measure mu. So we know that the value of the empty set is equal to 0, well, whenever the measure is not trivial, right? So we can perhaps add that here, that this is not trivial. So it is kind of perhaps obvious that it should be not trivial, but it is important to add it. So since 0 is the infimum of 0 is the infimum of, well, you know, any value which these functions may take, because you know the functions take values on this extended interval. So the 0 is the infimum. Well, we can write like this. Oh yeah, so this holds here. And the second property that we need to check is that if we have two elements in the power set, mu star on well, such that, you know, one is a subset of the other, we have that mu star is less or equal than the other one. So well, from this we know that mu of p is less or equal than mu of q, because this is a property of measures. So if this happens, then the infimum of, well, not exactly, this would only happen if those two were on the sigma algebra. So I rushed it. So all right, let's do it one step at a time. So let's do this by contradiction. So let's search for a contradiction, and by that I mean that we need to suppose that this one is strictly less than the other one. So this means because, you know, they are both infimums, so the infimum is something that you always need to remember. The infimum is the biggest lower bound. Oh well, it's also greatest lower bound. So if you have anything that is superior of this lower bound, then this won't be a lower bound. So this is not a lower bound. So since it is not a lower bound, then they should exist lower bound of the set. Let me write it like this: A in the sigma algebra and Q as a subset of A. Just the definition. So this is not the lower bound of this set, so it should exist some A star such that mu of AQ, let's work with some AQ, such that this is less than this one here, and of course this is more or equal than this value. So this is some AK such that there exists some AK such that some AK inside the sigma algebra such that Q is a subset of AQ. So and and this happens here. All right, so given that this is smaller than the greatest lower bound, so if this is a lower bound, then every value of of this set such that P is a subset of V should be around here, right? So if this is less than the infimum, then this is also, it happens that for every I don't know, V inside this set, which we may call P star, I don't know, P star, it will happen that this is strictly less than mu of B. So now you need to recall that since this works for every P element of P star, it happens, if you remember, that P was a subset of Q, right? We were working under this assumption. So since P is a subset of Q and AQ is a set that contains Q, then AQ will be inside P star, because AQ is an element of the sigma algebra such that it contains P by transitivity, right? So this implies that the measure of AQ is less than the measure of AQ, which is clearly a contradiction. So this happened because we were under the assumption that this is true, then its negation should be true, and so we arrived at this. So that works, that takes care of the second property of outer measures. Now we will prove the final property of outer measures. So suppose that we have some family, indexed family of elements, of course it should be countable, of elements inside the power set of X. So let epsilon be some positive number, and we have that well, for every k, mu star of pk is strictly less than mu star of pk plus epsilon divided by 2 to the power of k. So by definition of infimum, once again, there will exist some AK inside the sigma algebra such that PK is a subset of AK, and the value of mu on AK is less than mu star of pk plus epsilon divided by 2k. So it is the same argument that we used before to assert that there was some element here. So it's the same. Between these two there should be some element, which is now our AK. So there should exist some a something inside the sigma algebra, but since we are considering this index, we will maintain that index. So from this family here, this indexed family, what we are doing is that we are constructed another indexed family, AK, which is not only a subset of the power of X, but also a subset of the sigma algebra, in which we can apply all of our all of the techniques and properties that we know that work for sigma algebras. So since you know sigma algebras are closed by arbitrary unions, countable unions, we will have that it follows that the countable union of every AK will be inside the sigma algebra. And we also know that since every AK includes PK, then the countable union of every K will also include the countable union of every PK, right? So you need to see what's going on. You need to recall, keep in mind, and bear in mind what we are trying to prove. We are trying to prove that this property holds, the subadditive property. So we will need to find some upper bound of the value of mu star on the union, on the countable union of every pk. So we want that upper bound. So to do that, we are already on the right track because we are working an upper bound here, some sort of upper bound. So it's all going according to the plan. All right. So moving on, it holds that the value of mu star of this here is less or equal than mu star of this here. And why is that? Well, because of the second property that we proved here, right? So if we have inside a power set, if we have something that is a subset of the other thing, this order is maintained with mu star. So this is a subset of the power set. So we have two elements in the power set, so that one is inside the other, so this holds. But something that I didn't mention before, but for every we can highlight this here. This is a property that we will be using a lot. For every A inside the sigma algebra, the value of A is equal to the value of mu. So this happens because this is the infimum of every measure of B inside this, such that A is a subset of this thing here. But you know, by property of measures, it happens that if A and V are, you know, A is also an element of the sigma algebra. So if this happens, then this happens. So the infimum of every one of them is clearly this one, because you know A is a subset of A. So A is also in this set here. So this is why this happens. So this is this one is equal to just mu of this countable union. And you know that by the subadditive property of measures, this is less or equal than the value of the series here, right? But we were working under the assumption that every one of those is less than this thing here, right? So this also has as an upper bound, and we are getting our mu of pk that we wanted, plus A divided by 2k. All right, so we can have we can divide this series, one for mu of pk and one for this here, because the value on the left, I mean this this thing here, this series here is a convergence series. This is a convergence series. Let me add some page here. Alright, so this series converge and its value is just epsilon. So just remember, let me add another. The value of this here when k star in 1 is equal to 1. Alright, so this is equal to epsilon, and this is equal to this. Alright, so we're not assuming that this series here converges. It's not necessary. If it diverges, then it diverges to plus infinity, and we are still allowed to do this separation here because it will still be plus infinity, since we are assuming positive term with positive terms. Alright, so for the last step, since this value epsilon was arbitrary, it was any, we can take the limit of epsilon to 0, and we will have that this thing is still less or equal than this other thing. So to summarize, we have that mu star, well, I forgot to add the star here. Star, star, and star. So mu star of this countable union is less or equal than this series here of mu star of pk. Alright, so this is the final property of outer measures, and it follows that mu is an outer measure. Alright, so this completes the proof, and just to complete this video, we need some notation. Mu star was not, it has some proper name, some given name, and it is called the outer measure associated with the measure mu. So we will be continuing to use this way of converting outer measures from measures in the following. So if you have any questions, you can write it down in the comments, and I will try my best to answer them. We will continue with the second part of this lecture tomorrow.